Welcome back to class. Today, we are continuing our journey in Chapter 8, Rational Expressions and Functions. In this final lesson of the chapter, we will master the remaining two core areas, Section 8.4, Solving Equations with Fractions, and Section 8.5, Relations and Functions. Let's focus on finishing this chapter strong. When solving a fractional equation, we must consider its limitations. A fractional equation is undefined when the denominator of any expression equals 0. This means there are strict limitations on what values the solution can be. Let's look at an example. Consider the fractional equation 2 over 2x minus 3 equals 3 over x plus 4. To find the limitations on x, we set both denominators so they cannot equal 0. Therefore, 2x minus 3 cannot be 0, and x plus 4 cannot be 0. Solving these shows that x cannot equal 3 over 2, and x cannot equal negative 4. When solving fractional equations with different denominators, we can multiply the entire equation by the least common multiple of the denominators. This allows all the denominators to be cancelled out completely, making the equation much easier to solve. Let's solve an example. Consider this fractional equation. To clear the fractions, multiply both sides by the least common multiple, which is 6 times 2x minus 3 times x plus 4. Canceling the denominators yields 2x minus 3 times x plus 4 plus 6 times x plus 4 equals 6 times 2x minus 3. Expanding and simplifying both sides transforms it into a quadratic equation, which allows us to solve for x cleanly. Let's solve a complete fractional equation. Look at this expression. The question asks us to solve it, but first, we must state any values for which the equation is undefined. Since denominators cannot be 0, x plus 1 and x minus 1 cannot be 0. This gives us our initial limitations: x cannot equal negative 1 or 1. Now let's solve the equation by clearing the fractions. Multiply both sides by the least common multiple, x plus 1 times x minus 1. This clears the denominators and gives us 2 times x minus 1 minus 3 times x plus 1 equals negative 1 times x squared minus 1. Expanding and rearranging the terms leads to the quadratic equation x squared minus x minus 6 equals 0. Factoring this equation gives x minus 3 times x plus 2 equals 0. So, the possible solutions are x equals 3 or x equals negative 2. Since neither of these values violates our initial limitations, both 3 and negative 2 are the true final solutions. Now let's move on to Section 8.5, Relations and Functions. An ordered pair is a set of two numbers written in the form x, y. A relation is simply any set of these ordered pairs. For example, let's look at this specific relation named R. Every relation has a domain and a range. The domain is the set of all the first elements or x values of each ordered pair. For our relation R, the domain is 1, 2, 3, and 4. The range is the set of all the second elements, or y values. For R, the range is 4, 7, 10, and 13. Notice that these values follow the linear rule, y equals 3x plus 1. One powerful way to visualize a relation is to use a mapping diagram. In this diagram, the area on the left always represents the domain, while the area on the right represents the range. The arrows show exactly which member of the domain is paired with which member of the range. Let's look at a creative example. This mapping diagram represents the relation f. Our domain contains 1, 4, and 7, and our range contains y, w, and k. Following the arrows, 1 maps to y, 4 maps to w, and 7 maps to k. This gives us the complete set of ordered pairs for relation f. Relations can also be plotted on a coordinate plane. Here, the domain is represented on the x-axis and the range on the y-axis. Graphs are most useful when you have continuous sets of values, allowing you to connect points with a smooth curve or a straight line. Let's look at a creative example. This graph represents a continuous relation. The relation is defined by y equals 1 over 2x plus 1. The domain is restricted from -4 to +6. Notice how the solid line smoothly connects the starting point and the ending point. A relation is any set of ordered pairs without restriction. However, a function is a special type of relation. In a function, no two ordered pairs can have the same x value, but different y values. This means each member of the domain maps to a unique member of the range. Let's compare these two diagrams to see the rule in action. On the left, each input maps to exactly one output. This is a function. On the right, notice how the input 2 splits and maps to both a and b. Because one x value goes to two different y values, this relation is not a function. Let's practice determining whether a mapping diagram represents a function. Look at mapping A. Our domain elements are 1, 3, 5, and 9. Notice how the input 3 splits and maps to both x and z. Because this single x value has two different y values, mapping A is not a function. Now let's examine mapping C. Our inputs are the same, but the arrows are different. Notice that every single member of the domain maps onto exactly one member of the range. Since no x value branches out to multiple outputs, mapping C successfully represents a true function. Let's practice expressing a function given as a set of ordered pairs into an equation. Look at this function f. It consists of pairs 1, 1, 2, 8, 3, 27, and 4, 64. Let's find the mathematical relationship between the x values and y values. Let's look at the solution. Notice that 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. Therefore, the relationship between x and y is y equals x cubed. The domain is simply the set of first elements, 1, 2, 3, and 4. Combining these facts, we can write the function in formal set notation as shown in red below. Think of a function as a rule or a machine. It takes an input value x from the domain, processes it according to a specific rule, and then outputs a single distinct value, f of x, in the range. Let's visualize this process using a creative function machine. When referring to a particular value of a function, you simply replace the x with that relevant number. In our machine, replacing x with 4 gives f of 4, which equals 14. Similarly, you can substitute whole expressions into a function. For example, if we replace x with x plus 5, the expression becomes 3 times the group x plus 5 plus 2. Let's solve an example to find the range of a function given its domain. If p of x equals x cubed minus 2, let's find the range of p of x when the domain is the discrete set -2, -1, 0, 1, and 3. Let's look at the solution. The range is the set of all values of p of x for each x in the domain. So, the range equals the set containing p of -2, p of -1, p of 0, p of 1, and p of 3. Substituting each value into x cubed minus 2 gives the specific calculations. Evaluating these numbers, we find the final range is -10, -3, -2, -1, and 25. Let's learn about the equality of functions. A function f is equal to another function g if and only if their sets of ordered pairs are completely identical. This means it is not enough for their equations to be equivalent. They must also share the exact same domain and range. Let's look at an example with a creative twist. We have two functions, f and g. Function f is defined by x squared minus 9, and function g is defined by x minus 3 times x plus 3. Both functions share the exact same domain set, -2, 0, 1, and 3. Since their equations are algebraically equivalent and their domains are identical, the two functions are completely equal. Finally, by substituting these domain values, we find the range of f to be -5, -9, -8, and 0. Let's solve an advanced rational function problem. Suppose v of x equals x squared plus 2 over x minus 2. First, let's state any restrictions on x. The function is undefined when its denominator, x minus 2, is 0. So x cannot equal 2. Let's look at the graph of this function on the left to see the restriction. Now for part b, let's evaluate v of -2. Substitute x equals -2 into the function. The numerator becomes -2 squared plus 2, which equals 4 plus 2, or 6. The denominator becomes -2 minus 2, which is -4. Dividing 6 by -4 and reducing the fraction yields our final answer, -3 over 2. Let's tackle an advanced function challenge, which forms the core foundation of calculus. Given that g of x equals x squared plus 2, find the difference quotient, g of group x plus h, minus g of x, all over h, in terms of x and h. Let's look at the geometric meaning on the left graph. This expression represents the slope of the secant line connecting 2 points with a horizontal distance of h. Now let's expand and simplify the difference quotient step by step. First, substitute the function rules into the numerator. G of x plus h becomes the group x plus h squared plus 2. Next, expand the squared group into x squared plus 2xh plus h squared. Notice that x squared minus x squared and 2 minus 2 completely cancel out. This leaves us with 2xh plus h squared over h. By factoring out h from the numerator, we can cancel h from both top and bottom. Our beautifully simplified final answer is 2x plus h.